Thank you, Bob. Good evening. So when I first talked to Bob about this lecture series, we decided we wanted to try something different to make this very audience engaged and interactive evening. So at some point, we'll ask everyone to get up and we'll be moving chairs and having some activities in the center. But for now, stay seated. Okay, so again, my name's Irene Lee. I'm with Project GUTS, which is a new program we started in January of this year. We received funding through the National Science Foundation Academies for Young Scientists. And one of the many goals of this program is to get younger students engaged in science and keep them interested in science as they go from middle school to high school and beyond. Okay, I have this upside down. Okay, so growing up thinking scientifically. With me tonight, we have three facilitators for our program. We have Paige Prescott, who is a science teacher over at Monte del Sol. Joshua Thorpe, over there, who is an agent-based modeler and a software development person before he joined GUTS. And then Greg Malone back there. And Greg, let's see. Greg was a facilitator with a program previously called Adventures in Modeling, and he was also a science teacher in the public school district over at Capitol. Okay, so for this evening, what we're going to do is I'm going to give an introduction to complex systems. What are they? Why do we study them? How do we study them? And then we're going to play some games, as I mentioned, that'll demonstrate different aspects of complex systems. Then we'll run some experiments with one of the tools, StarLogo TNG, that we use to try to understand complex systems. And we'll play a game as a quick review. Okay, so what is a complex system? Let's break down the words first. Complex is difficult to understand or difficult to predict. A system is a group of interacting, interrelated, or most importantly, I think, interdependent parts forming a whole. So you can think of a complex system as a group of these units or pieces that interact in a system. One thing that's unique is that at a different, from a different perspective, you can look either at the independent agents and parts, or you can look top down at maybe the bigger system. And what's interesting is that the behaviors on that large scale sometimes are difficult to understand or difficult to predict, given if you only know the rules for the individual agents. Okay? Okay, so let me pose this question. Why do you think it's important to learn about complex systems and the various approaches used to understanding them? Any ideas? Yeah?
That's what our economy is based on.
Our economy, yeah. Anything else? Why are they important? Yeah.
Possibly could also model biology.
Biology? Right. Okay. Let's see. Well, this ties in. Some of the most daunting global problems we face today can be studied as complex systems. Here are some examples. Climate change, pollution, the spread of disease, loss of biodiversity, and civil violence. Those are all things that have been modeled on the computer using agent-based models. And also there's some local things we see, traffic jams, forest fire evacuation plans. Those can also be studied using this approach. Okay, so how do scientists how do they study complex system? This is showing an agent-based model in which there are agents that are connected in a network. And one way people study complex systems is by creating a world, a virtual world, in which there are these agents. The agents have rules, they have connections to other beings, other people, specific behaviors, and then they let this model run in this artificial world to solve a problem. I'm not sure what exact issue is being studied in this image, but the idea is that you're creating a virtual world in which to study a problem. Okay? This next image is somewhat different. This is showing oceanic flow, and this data was captured using some mobile agents, actual sensors that were left to run within the currents that sensed position and temperature. So this is another way we can study complex systems, right? And then this is somewhat of a combination of the two. What we have here is a map of the city of Venice. And each of these, I don't have a pointer, each of these bigger brown spots represent places where there are people counting the ships, which ships go by. But they had incomplete data. They didn't know where ships were between the time they had been seen. So they filled in this model using agent-based, using agents. So these little arrows, red arrows, are agents that were given paths and behaviors, but they were linked to the real-world sightings. Does that make sense? So we can take a look at that. Oops. Sorry. Uh-oh. No. There it is. Huh. Well, it's not running right now. But when it does run, you can see the agents circulating within the map of Venice. Okay, so the process we used is a computational science process wherein we select a real-world problem to investigate, and we simplify it into, we reduce it into an idea which we can model. So rather than studying global warming on a global basis, maybe we're looking at local temperatures and how those local temperatures are affecting vegetation, and thus how that might affect population of animals that eat that vegetation. So we'd reduce the problem to something much smaller and translate it into code, into a computational model. And for that, we teach a language called StarLogo and StarLogo TNG. And the logo, the turtle is our representative of that. The next thing that you should do, one would do, is parameterize the model, find out what variables you want to study, what variables you think are important. Maybe it would be the temperature or the amount of water in the ground. And then your model becomes an experimental test bed where you can change these variables and run it over and over again. So you run these simulations and you collect data, output, and then you interpret that data and see, well, does that data make sense? Does it match anything in the real world, or is it totally askew? And if it does not match a real world situation, the data that you capture in the real world, maybe it's time to start back around and look at the model and see if it's an appropriate model for what you're looking at. Okay, so I wanted to talk to you a little bit about the tool we use and the paradigm. In the StarLogo world, there's an observer who sets up the world, instantiates the creatures, puts them in their original positions. And then there are the turtles themselves, which are the agents, and they have behaviors. And the patches are the squares that make up the environment. Here's a simple example. In this world, there are rabbits, which are kind of dark, but you can see their shapes. And there's grass growing. And over time, the rabbits either eat the grass or they end up dying, and the grass continues growing. Once the rabbits have eaten enough grass, they have enough energy to reproduce. So when we create a model like this, we instantiate the characters, we give them behaviors. In this model, the patches or that are growing the grass has a behavior, and we can run it again and again. Do you think we'll get the same answer every time we run it? Any ideas? No? Why not?
You've got that embedded into the system.
A lot of rabbits?
More rabbits,
Uh-huh.
and
Then less
they
grass.
could, yeah.
Well, what if I kept all the variables where they are and ran it again? If I weren't... Do you have any ideas? No? Maybe we'll see some examples later. Okay, so the model is a representation of the interaction of animals in a real-world setting, but it is only that. It's a representation, and a limited one. And the goal of this model is to gain an understanding of how the model's results relate to the real world. We aren't writing predictive models using this tool. We don't want to know what's the temperature going to be in Nome in 2 years from today, for example. We try to see patterns and trends that develop based on the interaction of individuals in this world. Random factors are built into the model that can cause results to be generated differently when the model is run repeatedly. So an example of that is walking. The creatures in our world don't walk in a straight line. Sometimes there's a little bit of randomness in their walk, and thus what might happen? Does anyone know?
It sort of follows sort of a random path.
You could follow a random path, and would they bump into the same people if they followed a random path?
Probably not, or
Right. So in some of these models, there's interactions that happen when you bump into another agent in the world. And based on this idea that there's a randomness in the walk, you might bump into one person one time you run it, and then you run it another time, and maybe you're bumping into someone else. So there can be slight differences even when the variables are set the same in a model. The other thing is variables can be changed by the user to run controlled experiments with this tool. Okay, so there are various kinds of models. There are very simple idea models, which are the models we typically write. In this example, it would be a predator-prey model, and you would not specify what species the predator or the prey were. You're just capturing something about something about behavior of predator and prey. In a minimal model for a system, you might now say, okay, we're going to study wolves and caribou. We might not have a setting we might have a generic setting that model is running on. And then there are full system models. And that could be a wolf and caribou within a specific section of the Yellowstone Park. Okay? And we tend, in Project GUTS, to work more in the area of idea models. As you go down this schema, you get increased amounts of complexity and detail in the model, but you also get very specific and less generality. Okay, so does anyone have any ideas why it's better to run some of these things on the computer rather than in real life? Yeah?
because if you put like 500 rabbits within like a bunch of grass, they don't just die.
Uh-huh.
Yeah, well, some things might be dangerous in the environment, you wouldn't want to, harm anything, like.
For example?
Ethically. Like, there was a model I saw recently which was toxic waste and how it affected fishes in the ocean.
Mm-hmm.
So if you actually tried to carry out the experiment in real life with fish and toxic waste, it'd probably be a bit immoral, whereas this
Mm-hmm.
is just animation, so.
Good point. Okay, so often the experiments are too dangerous to carry out in real life. They're too expensive. They take too much time. We can condense a year's worth into a couple minutes.
There's something to be said about studying real world events, though.
Yes.
Because in situations like a forest fire evacuation model, there is human and animal irrationality that kicks in.
Correct.
And if you don't have the constant of the irrationality built into your model, the results will be completely different.
Mm-hmm. Good point. Okay. Okay, so now we're going to talk about some characteristics of complex systems. Greg, you were going to start off?
Sure. Am I up?
You're up.
Good. What do we have here?
So you're just on the
Oh,
first
yeah,
one.
you got
Okay,
the
there.
mic. Okay, so the thing about complex systems is that, first of all, there are natural systems in the world that are complex. So a lot of these things you'll just intuitively go, oh yeah, that makes sense. The problem is, of course, that even though a lot of things make sense to us intuitively, they've never been studied much. So that's what we're doing now. Some of the primary aspects of complex systems you can see right here. For instance, they're a leaderless system. Nobody's in charge in general. I mean, if you think about our world, we've got governments, but is anyone really in charge of everything? No. And yet, somehow this world is bubbling and boiling and advancing and retreating and doing all these interesting things. So it's a leaderless system. The rabbits and grass example that Irene just mentioned is a great example too. Rabbits aren't thinking about, gee, I wonder how our population's doing today. It just happens. This second bit here about the emergent patterns that develop from the interaction of the agents. You know, we see this all the time, but because we don't really analyze it, but we just simply hear about it or think about it. We hear about, for instance, there's a sudden infestation of a nasty little beetle that's in all the trees, right? And the next thing we see is something emerging in the landscape. What would that be? Dead trees. Remember that? How horrible was that a couple years ago? And that's a perfect example of a system where the agents, these little bugs, got in there, did their thing, and next thing you see these patterns forming. And from an airplane, you can even look down on the scene and see these interesting patterns forming. And then as nature took over and nature does its thing, and humans got in there and started hacking away, we see more patterns evolving. So that's the idea that patterns emerge. They're not always something that you'll fully recognize. They don't always look geometric and all that, but they're definitely patterns, and if you watch them over time, that's a key point. This nonlinear aspect of complex systems. Linear, would someone like to venture a definition of what linear means? Not just
line.
Like a line. So it's kind of like predictable. It's like, boom, I do this, I go one step, and now I'm here, right? I move this chair, and all the other chairs stay where they are, kind of predictable stuff. Nonlinear, what would you want to, I'll pick on you now since you've opened up here. What do you think nonlinear might imply?
Not in line.
Not in a line. Yeah.
Very
that's
good.
Pretty literal. Well, nonlinear, anyone else want to venture an idea about nonlinearity of systems?
Unpredictable.
Unpredictable, there you go. For instance, let's say someone walks in here and they've got the flu, right? And that could happen. It's probably happening today. It probably happened yesterday, wherever you were. And you shake this person's hand, and something gets transmitted, but you don't know it at the time. But what happens is, let a few little more handshakes happen and get across town, and the next thing you know, it's not predictable exactly what the result of that little handshake was. You can model it. You can model how a disease or an illness spreads through a population, but that's a kind of an example of nonlinearity. And then the self-organization. This is the part that I've always just been tickled about, because how in the heck do animals know how to do what they do? How does a baby know I need to now flip over on its back or on its stomach? How do systems get themselves organized? Certainly there's nobody in control. We're going to see some good examples of that in a few minutes. Okay, this page button?
It's the left.
Left button.
Oops.
Ooh, let's magnify. Oh boy, now we're having fun.
That one.
Oh, down there.
Yeah.
Oh, left click. Cool. Okay, so we talked about that. So you don't have this update slide? Oh, there
Oh
you
yeah,
go. Got
yeah,
it.
they're there.
So we'll look at this as an example of a leaderless system. I know probably most of you right now are thinking, wait a minute, there's a bird leading this thing, right? Isn't there usually a bird that leads the
Keep
flock?
shifting the pattern.
Right? I mean, you've seen them in the V, right? And there's somebody out there in the front doing this, and everybody's following. I mean, according to biological research, it's not necessarily a leader there in that system. There are some instincts they're following. This ability to flock and form these patterns is an example of a leader of the system. Do we have a link to a computer model on this or no?
Yeah.
We do? Okay. Where is it?
Go ahead.
Next. Well, let's look at this first. What's going on in the rule systems in the minds of these birds? We'll take birds, it applies to fish, it will apply to a herd well. How do they know to form these patterns and get along with things?
There's a model to run later. There's a model to run.
On this, 3 concepts. I know birds aren't really thinking this, but they're doing it.
I think it's after the
screen.
screen.
Separation. Like the one bird says here to avoid steer. Okay, so the idea is, okay, I'm flying. Steer to avoid crowding too close to a local bird, right? Okay, simple rule. Don't get too close. But get in alignment, more or less. So steer towards the average heading of your local flock mates, right? So I see the birds around me, and I say, oh, they're all kind of tilting to the left now. I guess I got to start tilting with them in an average, right? And then finally, this idea of cohesion, which is kind of like the opposite of this, is but still move toward the average position of your flock mates. Well, so move forward, but not too close, and kind of go in the same general direction. Now, listen, that sounds really simple, and I'm sure every one of us could have figured that out on our own. And yet, when you see a flock of 1,000 birds migrating, and they're all forming this interesting pattern, and they all seem to know what they're doing, it's actually a leader of the system. So, can you fire that up? Yeah, do we have an internet connection in here? Oh, Shawnee. Nice. Okay, this is a little computer model. I don't know what's driving this. Do you know what's driving this? A Java, probably some kind of Java app. Okay, and the birds are following those rules. In fact, that previous slide we just saw with the rules that they think about, the cohesion and separation and alignment, this is on the same website. And so this model has been written, and these birds are basically just following those rules. But there is no one bird saying, we're going to go this way or that way. So that's why they're probably just flopping around. But you can imagine that if they were looking for bugs in the night, right? The sun's setting, the bugs are out. If you've ever lived in the Gulf Coast, you know what I'm really talking about. And they're kind of just on the prowl, and one of them goes, bugs, and just starts heading that way. The others follow the rules, and there they go. Okay? Go ahead and scroll down that if you don't mind just a little bit, just to kind of show what the rest of this page looks like. Yes, and this is explained. Just want you to see the actual studies being done on these things in this particular group. Going down a little bit further, just I think there's a piece down here, and there are things that we're looking at there. So these are the guiding principles behind that model. Okay. Any comments or questions about that? Do you think fish follow different rules or similar rules? What do you think? Similar, yeah, got to. Pretty much in the same business. You throw in a shark in there, or in this case, throw in an eagle or something that might be messing with the flock of birds, then there are additional rules come into play, like stay alive, right? But somehow maintain the flocking or the schooling of the fish. Bueno. Okay, let's go back to that. So, okay, here we go. Nice. So, termites. Surely, right? Now tell me, this is true, isn't it? There's a queen termite that tells everybody, let's put the mound here, and I want it to be this tall, and I want it to be this general shape, right? Is that true? I mean, there's somebody in charge, right? Queen, you've heard of it. The queen bee, the queen ant, whatever. What does the queen do? I love telling my granddaughter about how the female sees these all the ones in charge. That's pretty cool. She loves that. When I told her about chess, I said, the queen's the most powerful piece on this chessboard. She goes, you're kidding. No. So, anyway, the termites. Termites are nice little species to model in a very simplistic way, and that's the beauty of it. A model we're going to look at in just a minute follows some very simple rules. You imagine that there are little wood chips laying around, and the termites have just a couple rules in mind. There's no leadership, but they have this programmed logic that says, I wander around until I find a piece of wood, and I pick it up. Then I kind of wander around until I find another piece of wood, and I take the one I'm carrying and I set it down next to the one I just found. Then I start all over again. Now that's really simple. Is it even likely that anything could emerge out of that, other than just a bunch of stuff being rearranged? We didn't think so. Let's fire up that model and have a look. And if it doesn't work,
Just give it a minute.
Get it going.
Say okay?
Sure. You're getting a peek under the curtain here of a Star Logo program. Thank you so much. Yeah, exactly. There you go. All right. This is a model called Termite mounds. And so hopefully they'll actually start building a few mounds. You want to hit setup? Now, before we run it, you might have seen some little dudes appear right here. These are little turtles in this, but in our case, we're going to call them termites. And so, Talia, if you would, hit that forever button. Forever is a long time. Oh, pull it out and speed it all the way up. Crank this thing up. Please. Thank you. There you go. Okay. So, we see here that they're following these rules, and what is the first thing you start to notice?
Mound's being like, take it away.
Okay, some things are being moved and relocated, and are we getting some piles started? It's not one mound yet, though, is it? I can remember actually seeing ant beds when I was a kid, and where I lived, and these red ants would have these. You could see all these kind of multiple mounds appear. Now that I think about it, that's exactly how it worked. And suddenly there was just one big mound. But as you let this run for just a little bit, and tonight I'm going to do a little driving on this for a second. So one thing I'd like to, I see, we're not seeing the yellow color here, but that's okay. I want to zoom in on this a little bit so we can kind of see some of what's going on here. And we'll just kind of concentrate on that space there. Now, if you imagine just for a second that they're following the rules we discussed. If I find a piece, I pick it up, I walk out, find another piece, put it down next to it. You can see that we've got a mound growing right here in front of our face here too, that might obscure the view any minute now. But you can see actually they're taking pieces off the mound too, right? That's still part of the rules. It's still part of the rules. If I find another piece, I don't care where it is. I pick it up and I move it somewhere else. So you'll see these mounds kind of rising and falling. But over time, eventually, and we'll get the big view again. We can see here, and I'll go ahead and do a little magic. You can see here some features are starting to form. All right? We can let that run for a while. And eventually, can you predict what is going to be the outcome of this model if you let it run long enough? Any of you? Okay, hang on, Arlo. Yeah.
One big
One big mound? You agree with that?
Yeah, and then because they've been taking the stuff out to build that big mound, there'd be a lot of little bits or a big bit above.
The rules of disassembly with the big mound begin to disassemble into smaller mounds.
That's a really great question. And if we had a little bit more time, I'd love to show them the other termites model. I don't think
To being flat like it is and how bigger flat spaces are opening up.
Yeah.
It
What?
actually level itself.
Yep. What you'd find is the big mound would form, but it would drift around. And kind of its shape would kind of change a little bit.
Greg, how many termites are in this formation?
This particular one, I don't know. Let's find out. I'm guessing in this particular example, we'll just go right over here. In fact, let me do this so we get a better view. Let's go to setup. Ooh, right there. 100. So you see right there at the top, this model starts is when you do the setup. It'll create 100 termites and get them rolling. What are these? Oh, 150 with it? I don't know. I didn't like this model. In fact, I didn't see this mound building model till today. And I thought this is so cool, we should look at it. Looks like maybe 250 total. Although actually I'm thinking here, yep, that's right. Some of them I think are doing the initial setup of the landscape. And then the others join them and they just take off and do their thing. All right, so Talai, would you switch us back to the PowerPoint? Actually, I think that model needs a little work. Did you notice they were digging holes also? Stuff was dropping into the ground. Something wrong there. Something not right. Okay, is there more? How are we doing here, Irene? Oh, there we go. So here we go. We can see our little fellows there doing their thing. And we saw that live just a moment or two ago. It's really creepy looking, isn't it? That's creepy. Okay. So, here we go. Magic. Go. I see a hand. Ooh. Oh, I'm actually, no, cancel. All right. Next slide. It's not behaving.
Nope.
So, Talai, why don't you try the right arrow? Just get us off that slide. If you don't mind. Ooh. Spinning balls. We've got all kinds of fun things going on here. Pay no attention to that math equation on the slide.
Josh was going to tell
Josh, I'm going to let you handle nonlinearity.
So nonlinearity is another of the main principles that we run into in complex systems. And this is the idea that even though it would be really nice if the world was easily predictable and you do a small little change and you get a small little result, fact is the world is not. It's not linear. And so nonlinear in mathematics is what we were talking about earlier, which is the idea that left click.
There you go. Oh.
Oh, right click. Can we go back? The idea that if you had a linear world, then f of a plus b would equal f of a plus f of b. But something as simple as the square function 2 plus 3 squared is not the same as 2 squared plus 3 squared. That's all that's showing. But in general, the idea is, in a linear system, you make a small change, and you'll get a small change. You take a small change in the input to a system, in what you start with in the system, and you get a small predictable change in the output. But with a nonlinear system, even a small change can produce a very large change. And in fact, depending on at what part of the system you put that change in, you could have it have a big impact or no impact at all. So and basically this is why complex systems are very interesting. If they were simplistic and we could take apart their parts and look at each part and say, oh, this works this way, thus it must work this way, that'd be pretty boring. But the really cool part of complex systems is that you actually have to look at all of the parts together. It's a very sort of holistic concept. Keep hitting the button and it doesn't. And here's just one very simple example, but population growth is unchecked is an exponential process. And what we can see here is 5 time units of growth down on this part of the curve is very different from 5 time units over on the right side over there. And I believe that's the last of my slides. But did anybody get that?
Oops. Back one? So another characteristic of a complex system is self-organization. There's no one that's telling the agents or whatnot to arrange themselves in a certain way. Just by virtue of the rules that are in the system, sometimes self-organization occurs. So let's see, let's look at an example. Do you want to? Okay. This is a classic example called the Schelling segregation model. And what Schelling did in 1971 was he was studying neighborhoods and how neighborhoods were formed. So he was working on a table with his son, and he had pennies and a grid diagram. And he made up certain rules and moved pennies according to those rules. So the primary rule was to look at the 8 neighbors around you. Say you're on a grid, 3x3 grid. So you have 8 neighbors around you, and you say, okay, I'll be happy living here if maybe 2 of the 8 people are different from me and the other 6 are similar to me. If I made that rule.
I think it's the reverse though, actually. I'll be happy if 2 of the people around me are the same and 6 of the people are different.
Or different. Or the other way around. You could
Yeah.
run it many different ways. And then what happens if that rule changes? You know, what if I'm really picky and I want all but one of the people who live on the block around me to look like me? What would the world look like then? So do you want to try to bring that model up? Ooh, can we see the different colors? Or are we only seeing one color?
Yeah, there's no red showing up. So, yeah, change it to blue. All right, yeah, blue.
Quick fix.
Rewrite the code.
Rewrite the code.
It's like Shakespeare. Backstage.
Go Talia. Much better. Yay! Okay, so in this world, Talia, could you put the percent cover down to PCT cover about 40s or 30s? Yeah. And put the percent happy to lower. Okay, so the percent cover and then hit setup is how much of the world is covered by these beings, yellow and blue. And the percent happy is the rule. So I am happy where I am if 7% of the people are like me out of the 8 spaces around me. So go ahead and run that with the other go. It doesn't matter. Yeah. So they're happy. What does that world look like? Is it pretty mixed? Yeah? Okay, now go ahead and change the happy percent to something like 20, 30. Good. And hit that.
Hit setup.
Oh, sorry, hit setup. And then. So what's happened now? Some forming. Okay, do you want to turn the happy percent up some more? Okay, and setup. And to go. See? So even if I thought I was open-minded and said, I only need 50% of the people around me to be like me, you see definite neighborhoods forming, segregated neighborhoods. So that was surprising that such a low threshold would cause this effect.
And it's the same number of different color agents?
Mm-hmm. Yeah. This is Schelling. Conway, yeah. Different rules. Mm-hmm.
But who had the priority here? Or were they collaborative?
Boy, I don't know what year Conway.
Probably has the priority. This is a overall field called cellular trauma.
Yeah.
Mm-hmm. Conway.
Conway, I think.
When was that?
I don't
Ford?
know.
Okay, okay.
60s.
Okay, so I was just using this as an example of self-organization. No one said to form neighborhoods where people are just like you. Okay? Great. You want to move on? Okay, so again, the 4 characteristics we've talked about. The systems are leaderless. Emergent patterns occur, or patterns emerge. The system is nonlinear, and sometimes there's evidence of self-organization. Okay? Okay, time to play some games. What we've been waiting for. Thanks for sitting through that part. First, we're going to play a game called Sword and Shield, and Paige is going to lead that. But first, we need to move chairs out to the edge.
This is a participatory activity, so, and we need all the chairs to the edge. So we're gonna... All right. Are you guys playing? Yeah. Okay. We're all playing.
Don't tell them. Don't tell them.
Yeah, don't tell them. No. Yeah, you can't tell. Sorry. Sorry, I forgot about that rule. Silence. All right.
Can you repeat the rules again? Just
Yeah. So the rules are, you will pick one person that is going to be your quote-unquote shield. And you will pick another person that is your sword. And you must maintain your shield between you and the sword.
Equidistant.
Not equidistant.
Just between.
Between.
You signal if you lost your shield somehow?
No,
Nope.
signaling, it's everybody's going to be moving at the same
And
time.
this is anonymous, right?
Yep.
Anonymous.
Right.
Uh-huh.
And I'm going to stand by the, I'm just going to keep that safe.
So
Okay, I'm
Irene,
not
are
going
you
to play.
playing? Irene's not playing. Can't pick her.
I'm going to
Okay.
keep this safe.
So, just take a minute and identify the people. Okay.
Silently.
And are we ready to play? All right, let's get started. Play.
No running. Uh-oh.
Someone's gonna get run over.
Not me.
Susan.
We're frustrated over here.
Yeah, when your shield gets to the wall, you're kind of...
I have a complex here.
All right, is everybody freeze? Is everybody satisfied? Is your sword protecting you, or excuse me, your shield protecting you from your sword? Yes.
No.
No, not me.
No? Raise your hand if your parameters are not met. Oh, so we have some instability. All right. So take a look at the pattern that has emerged. Okay. We're going to play again. All right. So let's go back into kind of a circle here. And now you're going to pick 2 different people. Again, one sword and one shield. And Irene is not playing?
I'm not playing. I'm
Okay.
guarding the equipment.
All right. So we ready? You picked your 2 people? And let's start.
Uh-oh.
Okay, freeze. How many of you have your parameters met right now?
Met?
Met? You're happy.
You're happy.
All right, so how many of you are not happy right now? Okay.
Ah, okay.
So take a look at the pattern that has emerged. And
What kind of things were you noticing? What was happening?
We were herd mentality.
Herd mentality. Did anyone tell you to do that? Anything else? What other patterns formed?
Surprising velocity changes.
Grouping.
Groupings. Okay.
Yeah.
Okay.
Ran into
Environmental issues, running into barriers. So what determined where you stood? Was it just the two people you chose?
Always the rules, because then the people you were choosing were connected to other people, so it's have to align itself with certain shape.
Stay away from the wall.
Uh-huh.
You said they would have space here.
So were there separate groups that had nothing to do with each other? Yeah?
What does this do in an unbounded system?
What do you think?
It does, doesn't it?
Huh?
It expands like.
Perhaps. Okay, let's look at a model. So we actually have a model of this. It's a model, again, the color's not really too good, where you can change the number of people. Say there were about 20 of us. And you can set up randomly. And then the computer has assigned each of these turtles a sword and a shield. And we can see what happens when we run it. And let me turn the speed down a little bit. Okay, go. So what kinds of things are you seeing? Uh-huh.
When there's one outlier.
Uh-huh. And I can change the number. Say it's a larger group.
Expect them to queue?
Did you guys queue?
I was wondering if you'd expect them to queue, but you can't with different individuals choosing the same shield or something.
Uh-huh. So what aspects of complex, or what characteristics of complex systems do you see in this example? What sorts of? Mm-hmm. Self-organization, okay.
You can see that one, so it keeps venturing out, but then following the leader.
Uh-huh. And one thing that's cool in this model is you used to be able to click on, oops, could grab a turtle. I'm not fast enough. And you can move it around and see how it affects the whole group. Oh, it didn't like that. Did I crash Star Logo? Okay, we'll go back to the presentation. Okay, so now we're going to play a game using handheld Palm Pilots, and I think Josh?
Yep. So this game is called the Prisoner's Dilemma, and it's a real classic game.
Yep. Thank you.
And Prisoner's Dilemma is you and your confederate have been arrested by police, and you're in two separate rooms, and you have to decide whether you're going to cooperate or defect. That is, are you going to say, he did it, or are you going to say, I don't know anything about it? Now, if you both say, I don't know anything about it, you're going to get one payoff, one score from the game, and if you defect and your friend doesn't, you're going to get a different score, and if you both sort of say, he did it, and point at each other, you get a third score. So part of this game will be just learning about the rules, or the dynamics of a game that have what's called a payoff matrix. But I'll let you. All right. So first thing you should do is the one that's called prisoner. Click on that one, and you need to put your And there's a little area that says April.
Mm-hmm, good.
Oh, I'm sorry, turn on the power first, which is the little green button. And then once you turn on the power, you should see a menu.
And if you don't,
you hit
the
the
house. Click on the little house there that you see. You can take the stylus out. You pull the stylus out. And just tap on the house. Oh,
Oh, good. Fantastic. Glad you could be here.
So the should one that says prison.
Give you my card.
Okay.
Click on prison. Tap on prison. And now it's asking for your name. There's a ABC in the bottom corner. Click on the ABC, you'll get a little keyboard.
Fantastic.
Is there something coming up with guts in April, Anna was saying?
And when you're done,
Yeah, there are a couple things going on. There's an expo in Los Alamos. Yours working?
Oh, yeah, I got it.
Yeah. Okay.
is everybody good? After you hit done, you'll be able to hit start, and we'll be ready to play.
Are you playing, Bob?
Okay, so everybody
Oh, there are. There.
Okay.
everybody got their names?
Oh, but you're Irene.
Still working on that?
Does anyone need help?
Anybody need any help?
Okay.
Hearing victory.
So the first thing you do is hit meet. And then
No, you have to select one of these first and then hit.
you hit who you're gonna play, and then you hit meet.
No, you pick your strategy first.
Oh. Okay.
I'm pretty sure.
All right.
Right, and then you hit hide, and then you meet,
Oh.
and then you hit meet.
So you pick what you're going to do
Yes.
before.
Yes. Yeah.
All right. So now you should be able to click on start, and you'll be given the choice to either defect or cooperate. So you have to make that decision, and then hit hide, which is the one in the middle, the button in the bottom middle. And after you select either defect or cooperate, and then you're ready to meet and play the game against somebody.
And what are we doing?
So it's a live. Yep. So I made my decision. She's made hers. One of us, one of the other of us will hit our both. So we press.
Do you want to be Bob?
Sure.
Okay.
Here you
So
go.
I put you down for cooperate.
Oh, thank you.
We both press this?
Only one of you presses meet.
Oh, I guess
Did you press it?
If you want to
That's good.
Did you?
It said, please don't move.
Okay, try again.
Which, you do it.
the show button, change right.
There you go. You and your opponent have both cooperated.
All right.
Okay, so I hit hide now.
And then we can meet.
It's okay to change.
Go ahead and hit meet.
Okay.
So what do you do next?
Thank you. We've both cooperated, and for that, we have a score of 0.
No, it says you have defected, but your opponent has cooperated. I
You defected on me? I would have never have thunk. Around and we meet people. Okay, so
Yeah, say okay.
who wants to meet? Who wants to meet? Anyone want to meet? Do you want to meet? Ah. Oh. Yeah? Mm-mm. No. Why?
I can't get out of it. But when
You
I press OK,
and
nothing
your-
happens.
Oh, there you go.
Okay.
Oh, me until you're in the corner.
There we go. First one to 50.
So when we both defect, we only get 1 point.
Okay.
I'm not going to play with you.
Shall we?
Sure, hold on. You can change it each time. Okay, thanks. Thank you. You want to play some more? What are we getting for cooperating?
3 points.
We can play.
Okay.
You can
You want to cooperate?
Parameters before each meeting.
You want to play?
Yeah,
Are you being nice?
Hitting show, that'll allow you to change.
Okay.
Hit show.
Oops. Try again. If we keep on cooperating, if we just play really fast, we should be able to.
Do you want to play again?
You're at 50?
No, I mean, I can't imagine being
Okay, we're at 12. Okay, sorry, okay. Okay, we're at 15.
Sure.
Are you a good cooperator?
Yeah.
Okay. How many points do you have?
9.
24. Haha. You want to play?
I believe. Yeah, but let's see.
There you go.
You have 55? We've got 54 over here. We have a winner.
I gave her 30.
Did you? Okay, where's Josh? No. We have a winner.
She got to 50?
54.
Wow. What strategy did you use? Do you know? what were you doing? Were you changing your cooperate defect a lot, or did you keep that constant? I know you defected against me. Is that right?
Were you playing with a strategy, or were you no? Oh, okay.
No, but so did you just keep defect as your number one? So has anybody looked at the scores that people were getting when they both cooperated, or
Nobody wanted to meet me.
so what happens when two people cooperate?
We were on our way.
3 points.
Both people get 3 points.
And they cooperate,
So 5 points if there's a cooperate defect, right? The person who defects against a cooperator gets 5 points. The cooperator gets 0. And how about if both people defect?
1 point.
1 point.
1 point each. Okay. So now you're starting to get a little bit of a sense of how this game works. So in a room full of cooperators, it pays to defect. Right? So we had a lot of cooperators. I was cooperating, and I gave her 5 points. I got 0. So what do we do next?
Okay, next you want to quit out of that game, and then you want to re-enter Prisoner's Dilemma.
Okay,
So you
how
want
do
to
we
go to
quit?
the top left and
Click on the Prisoner's Dilemma.
and hit exit.
Hit exit game. So Prisoner's Dilemma is at the top. You click
And
on
then-
it. There'll be an exit game at the sort of toward the bottom. And it says, "Are you sure you want to exit?" And you say yes.
Okay, and now we're at the start screen and we see the welcome, and click on the welcome, and we're going to set preferences.
Actually, go back
wait,
to prisoner first. Go
So we click on
Okay, sorry.
prisoner, and now there will be a welcome up at the top. If you click on welcome, then you can set preferences.
You have to put your name in again.
Oh yes, you do have to put your name in again.
I did.
But first we can set preferences.
Okay, so under set preferences, this time we're going to force you to meet the same person 3 times in a row before moving on.
So
that's where it says force, and then there's a box. Click on that box.
I'm lost.
okay, this is under set preferences.
Are you on set preferences?
No.
Oh, okay.
Right there, yeah. Click
Let's do done.
on the box next to force, it says it has a 1. Now if you
Okay.
should be able to.
Okay, welcome. Uh-oh. Okay, we can go like that. And then we go find prisoner, and then we go like that, and then we go set preferences, and this is the one we want to change.
Okay, is that the only adjustment we're making?
So what does it do
Just one
now?
adjustment,
Okay.
we're going to change to force 3 consecutive. So your cooperate. So the numbers in those 4 boxes should stay the same. They should be 3, 0, 5, 1. And once you've changed force to force 3 consecutive, hit OK.
Oh, okay. Let me do yours again.
And then you're going to put your name in again. Remember, there's that ABC in the corner.
But I assume the consecutive just means
Oh, cancel.
3 cooperative, or defective.
So you want to...
Yeah, it doesn't matter what you do. It just means that you have to play the same person 3 times in a row before you can go on to a new person.
So this one is force. So now we're all
Right,
forced
you'll
to
have to
meet
play
3
3
the
times.
same person 3 times in a row before moving to the next person. Okay?
Okay, so is everybody all right? So we put our names in. choose our strategy and hit hide, and we're ready to go.
And you can change your strategy between each meeting.
But you have to meet the same person 3 times and then, or each?
Yeah, it's actually choose your
We're not doing the changes.
Thank you. Okay, we can move along. Greg, you want to play?
Yes, let's do it.
How are you doing?
You want me in? You want me in? Wait, you go.
Okay, Josh, got a 51 over here.
Thank you. There's value in cooperating.
Greg.
Greg over here.
Probably shouldn't have done that.
And who's
Who else is 51? Okay, come over here.
I bet there's 2 different strategies.
So, Greg, what was your strategy?
Well, we just lived within the rule system, and 2 people cooperated till they got up to 50.
Now that's real cooperation. And what did you do? Were you changing between defect? Yep. Yep. So you just went around to a lot of people. Did you stick with cooperate, or did you stick with defect? Or you stuck with defect?
Yeah, it really worked.
Yeah, I tell you, if you've got a trusting room, defect is the best.
You're right.
The best, you know, if you got
Does that
a
work in
friendly group.
everything?
Oh no, I mean you get enough junior high kids together, and it's defect.
That's all they want to do.
That's all they want to play.
Yeah.
Okay, do we want to do the last version?
Okay, what's the last version?
The last version is you keep it with 3. No, sorry. That 3 consecutive meetings goes up to 5. And the one below it, limit to the first blank opponents, limit it to the first 3 opponents. So I can only, if I play Greg first, then I play Josh, and then I play Don, I have to keep on playing within that group. And I have to play each person in that group 5 times before I move on.
Okay, so we're going to exit the game.
Yay.
Up at the top, Prisoner's Dilemma, go to exit game, and then hit prisoner again. And then go to welcome. Set preferences. Okay, so now we have 3 consecutive meetings, but the next thing that we're going to add, or we're going to change that?
Yeah, we changed that to 5 consecutive meetings.
So the first thing to do is change the force to 5. So click on the force, and then hit the adjust button up twice, so you're at 5.
Just go with the force.
And then the next is limit to first. And right now it's 2 dashes, but if you click on that one and you change it to the first 3 opponents, limit to first 3 opponents, that's going to set you, up to 3. So it should be force 5 consecutive meetings and limit to first 3 opponents.
When I click on set preference, it just gives me to the prisoners it says about.
Okay, so you go here and up. And then this one goes to 3. Yeah.
So what does it mean? You have to stick with the same?
Meet someone, you have to meet them 5 times.
Okay.
And in a row. And you're limited to the first 3 people you meet. You have to stay within them.
Oh,
Okay?
okay.
Okay, you guys ready?
We have to put the name in again, right?
Yeah, you have to put your name in one last time, and then you're ready to go.
Hi.
Hi.
You want to play?
Sure.
I play nice.
You're not supposed to tell that ahead of time.
Yeah, you are.
You are?
What's the rules?
I'm proud of it. I don't know. I think I'll cooperate. How many times have we met?
I didn't count.
Data. Up 3.
I have 26.
That's pretty good.
Yeah.
Okay. Oops, we both hit it.
The other party does not want to meet you.
Okay, go ahead and hit meet. We hit meet at the same time. Okay, and one more time. Okay, there. So I have 16 and you have 36 because you've been what? Because I've been what? Defecting on me.
Oh, that's
Okay, I saw that.
Okay, anyone at 50?
Okay, so who's got 50 now?
You defected on me, Asher?
50 here, 50 here.
I thought so much more of you.
So what was your strategy? Sir?
Defect almost every time.
Defect almost. Well, why
Except
would
in
you?
situations where there was mutual cooperation, where we both knew.
If you knew that somebody was going to cooperate, you felt safe to go to the cooperate. Otherwise,
Yes.
defect. Okay. Why? All right. So let's open this group up a little.
Yeah, can we gather around?
Or gather around.
Or,
Any observations about this game? No.
There's a lot of attempted backstabbing.
he says, okay, louder?
Everybody was like trying to backstab each other. I mean, almost nobody cooperated.
Almost nobody cooperating. Yeah.
Everybody totally defected.
And see, I was finding a lot of peer pressure in my circle of people who were like, "Oh, you're being mean if you didn't cooperate." Yeah. So, like, my wife would have been really upset with me if I had defected. So, anybody find a good strategy to make a lot of points real quick? Yes.
You tell them that you're going to cooperate almost every time, but then you defect.
Okay, so convince them that you're a cooperator. Convince the other party you're a cooperator, and then defect.
Okay, yeah, if they were starting to defect also, protect yourself from losing points.
So you're protecting yourself by losing points from losing points. How?
Like when the first time, if they defected, they'll probably defect again. So switch yours to defect.
So, and then what does that do?
So that means you both defect then each other, and you both lose points or it remains to 0.
Right. So if you were cooperating and the other person defected, that person who's defecting is getting 5 points, and you're getting 0. And does that feel fair?
No.
No. It definitely does not feel fair. And if you both defect, what happens?
You get 1 point.
You both get 1 point. So that's like you're both sort of punishing each other, really, right? I mean,
except you're both benefiting.
You're both benefiting. That's true.
If you find out if you're in a good situation where you're defecting and they're cooperating, you just meet faster before they can switch.
So you just keep getting it while you can. Yeah, that makes sense. So let's
is there one sure way to rack up points real fast? Sure way.
Done.
Without ever losing.
We asked about 3 times if anyone else had hit 50 after I cooperated with just 2 people, Irene and Josh, and all we did was cooperate.
We just stood there and cooperated.
You did it openly. And we found through some hard knocks that you had to show. You couldn't be hiding your stuff.
Oh.
You had to show what your exact setting was while you played. So there was complete verification.
Oh, that makes it more honest. Yeah. So just really quick, when you look at the points that are being racked up, if you're both defecting, then the both of you are making 2 points, right? 1 for each of you. If you're in the defect cooperate, one person's getting 5 points, the other person's getting 0. So between the both of you, you're getting 5 points. And if you both cooperate, how many points are you guys both getting?
3, so 6.
So, yeah, 6. So depending on how many times you play, as far as cooperation, the both of you are getting the best score you can by both cooperating. But it feels a lot better to get 5 against 0, because then you're sort of getting something over on someone else. And I think that's what a lot of people really want to do.
So did anyone notice an impact when we went to having to meet the person 3 times in a row? Any change in how you behaved?
Well, more strategically, because you figured it'd be more random if you were walking around, so you would just would have set it at random because you weren't going to know what the next person's was. but you could sort of tell the mentality of the person by like the first, or first or second meets. So then, like by the second or third one, you would change yours to digitally make that.
So you had an idea when you were walking up, since you had already had a past experience with them, you had an idea of how they played, right? Is that what you're saying? Or is that a little different?
I think that's it, yeah.
So he would play him twice and would know what to play the third time based on how the opponent played to him the first 2 times.
So did anybody notice how we were changing the rules, what was going on in that? We were sort of fixing the situation a little bit, right? Because we were making you have more experience with the same person. So the first one, it was meet one person, go meet someone else, and you didn't really have a chance to get a sense of anybody, right? Does that make sense? But we kept sort of closing it down so that you had more and more experience with a particular person. And how does that change your strategy? And that's sort of a big question that a lot of people that study the game theory, there's a big difference between the way you play a random opponent and an opponent that you have been playing for a long time. Does that make sense?
Yeah. And this specific game, the prisoner's dilemma, is also used to study the evolution of cooperation. Why do people cooperate?
There's a future.
Longer future. Longer future? Excuse me?
Mutual benefit.
Mutual benefit? And how does that change as group sizes or get smaller, as people get to know each other better?
There will be more cooperation, less defection. I think.
Cool.
Unless you're really hostile.
Okay, so how does this fit in with complex systems? How would you tie that in? Any ideas? Talaya.
Complex electronic devices.
No, that's not it.
Okay, so what were some of the ideas of a complex system?
Nonlinear.
Nonlinear. Was this nonlinear?
Well, I couldn't plan every single time what I was going to do. It depended on who I was going to meet and how many times I was going to meet them.
So you didn't keep the same strategy.
No, you try and it doesn't work.
Okay.
The other person adapted your strategy.
How about any other ideas from those 4 topics? Was leaderless. Did we have a leader in this? Was there somebody who was going around saying, "You will play this way next"? No, we were all sort of our own boss, right? We're all trying to figure out our own strategies. How about organization? Were we organizing into anything?
Yeah.
Yeah?
Yeah, 2s and then 3s.
Yeah, and I know a lot of the people, there were sort of 2 different ways of getting 50 in this. One was to just defect and try to find a lot of cooperators. And the other strategy was to find somebody that you could sort of collude with, and the both of you just cooperate and just play each other. So those are different strategies, sort of organizing groups.
Great.
Okay.
Do you want to go around and pick them up, and I'll try to set up the computer.
Favorite day. That's fine.
Oh, I think if you click the model. Oh, it's your own model. Never mind. Put you on the spot.
I don't know if this is the last activity of the night or just about
Just
last.
about last.
So this one will be a little bit of a little closer look at a TNG model, and we'll explore some ideas with it here. So I'm going to get this kind of positioned about like so. And let's go back here to this. We're going to look at a model here called fish and plankton. Okay, and you might, well, I'll ask you what kind of system this is in a minute. We'll kind of zoom in there and see what we have. We have fish of all different kinds of colors, and you're not seeing all the colors I'm seeing here. I don't know what's with this projector, but it's sure not putting out the red. But anyway, you get an idea that there are different colors of fish. And the little green balls there, if we click one of them, we can see it's a plankton. That's number 248, that guy. And that fish right there is fish number 41. But there they are. And so, and when you set them up, they do a kind of a random scattering. And then you do the forever button to get them in motion. And let's just watch these guys and see what happens here. I'm going to back it out a little bit so we can see the whole system. Oops. Oh. All the fish are gone and nothing but plankton left in this world. Well, let's try that all over again then. Set up. and I'm going to ask you to tell me what the rules of the system are. In a minute, just kind of look at it. Think about who are the agents and what are the rules. All right. Arlo, I love it when you answer, but I want to give some other people a chance too. Yes, sir. What do you think?
If the fish eat enough plankton, they reproduce with more fish, and eat more plankton, and eat all the plankton, they die.
Okay. That's basically true. Let's look at this from a top-down point of view. You can see them all scrambling around there like so. That's a pretty fair analysis of the rules. Arlo, do you have anything to add to that?
Well, in this system, in the first system, we did that, and all the fish died off when the plankton happened. In this one, they get just up and running, just died off.
Okay. Almost, yeah, nothing, even though it says a forever button. Right. So I can tell you right now, that it looks like there's about 15 or 20 different colors going on here at the moment. You don't see the colors the way I do, but why do you think, what's going on with the colors? Let's explore that idea just for a second. Dominant fish? What, is it a dominant fish, really? I guess it is now. It's the only species left, right?
Whoa. Oops. Oh,
I don't know.
I don't know. No.
Oh. Ah, there you go. All right. Now I'll ask. So the question then is, number one, what are the agents in this system? How many agents are there, and what are they? What do you think? What do you think of that? What's one of the agent types? Purple fish. Oh, okay. So each color maybe is a type of an agent. Sure, that represents maybe a certain breed or species. Plankton's an agent. And so we got fish and plankton. We have an environment. Does the environment have any restrictions?
Well, they've got the walls, so they can't go, they don't have infinite space.
They have walls. What about, I don't see any walls on the top. Is there, oh, there's something going on there, isn't there? So let's see here. Every time I do a setup, is there a restriction vertically? Uh-huh. There is. So let's look under the hood for a second. Go over here to this program. And when these fish are first created, wow, the color is really going out on this. Check out here where we're doing the create fish. See that little piece there? We start off with 50 fish. And look at the first thing we do is we set their altitude for each individual fish to what? Yeah, in this case, between 1 and 30. Mm-hmm. So there is a limit there. Now, that's just only when they're being created. Now, when they get updated, it's here in the runtime area. We come over here. See, fish kind of do some things. They say, this is for the forever button here. So whenever you click the forever button, it basically makes them run this thing called move, up and down, reproduce, and do I need to die? Question gets answered for each fish, each cycle of this model. So let's go take a look over here at that. Now, since we were talking about the altitude, and by the way, this is an interesting way this kind of model is written. You saw an earlier version of TNG a while back, I think, that Irene was demonstrating, and the code was written in text, which is a great way to write program code, of course. This particular program uses these ideas called blocks. So you can move pieces and click them together, stuff like that. And you can actually make a function here called up and down. So here the fish, you see it says fish. The fish says I'm going to move up some random number, you know, a random 3, and then subtract 2, which means I can either go up or down a little bit. I know that's a weird way to express it, but if you think about it, that will generate either a -1 or a +1 or somewhere in between, or no movement at all up and down. And then it does a little checking here. If the altitude's less than 1, set it to 1. If the altitude's greater than 30, set it to 30. So this is what's so cool about modeling. And again, by the way, modeling, we're not really looking at reality here in the sense of, you know, if you were to put 50 fish in a tank, this is exactly what would happen. Not at all. This is just kind of it's not exactly a simulation. It is modeling because it's got the randomness to it. But it stimulates our thoughts to try to understand how the system might work at a real basic level. So what would happen if we tinkered with some of this, like the altitude, like their maximum altitude? Anybody want to make a suggestion? Let's hack this model.
20. Let's make it 20.
Set it down to 20? How about the little radical on that? Let's just put it down less than half of that. So 15. Is that okay? Let's do that. Now they're going to set up still with the 30 because we didn't change the setup. But they should very quickly be hunting their way down lower. And there they go. Can we make any predictions of how this system might behave here? Is there already a difference?
Well, the plankton on, because, I mean, you know, the plankton can never totally die out, because there's always going to be a random amount of plankton above the fish level. I mean, theoretically they can die out. That's like a chance in a million.
Are you seeing something characteristically different, though, about the way this particular run is behaving compared to what we were watching before? What's fundamentally different at this stage? They're not dead yet. That's interesting. Weren't we seeing explosive growth at some points where all of a sudden they just exploded into a big pack of fish, and there were only a few? Why were they exploding into lots and lots of fish, and why are we not seeing that now? Possibly.
The stable amount of plankton for the fish.
Yeah, it has to do with your mind. Sure. Well, just like Arlo said, just like you just said, the plankton are up there, the fish are down here. There's a little plankton that's drifting down, just enough to keep them going. But you don't see these explosive growths as though it was a nutrient-rich environment, right? Let's play with another, just while we're in the track. What if we made these numbers substantially bigger? Like 50. So we said they can go all the way up to 50. Whoops, did I just blow it? So I'll set altitude, let's get rid of that, goodbye. Set altitude to 50 if it's greater than 50, okay. Let's try this. So far, that's just what you'd expect on the setup. What's happening to the ones that are going up above the 50 line? Let me see if I can get this kind of level so we can maybe get a sense of it.
Oh,
any of them going up and above? Not now, they're not. In fact, let's do this. Let's go back to our setup, and let's set them to a random 50, just so they actually start some of them above the water line there, or above the plankton line, let's call it. Ooh, that was the plankton I just changed. Look at that, the plankton line.
Let's try that.
Changed the wrong stuff, didn't I? Well, that's true, interesting. So a lot of the plankton would be up above. But since that wasn't what I intended to do, let's put that back. That was the plankton I was playing with. Let's go back up here and set the fish. Okay, here we go. Set up. Ah, got a bunch of them up there in the stratosphere. What's going to happen to them? I think we get the idea. Now, it just so happens there are some other factors in this model that could be explored. Anybody want to venture a guess on what some of those things might be?
Well, I noticed that, like, right after the fish come into a big clump of plankton, they go swimming away all fast and they start to slow down until, like, when they finally disappear, and I guess it's dying, you know, they're really slow. So it'd be like their energy, metabolism there?
Well, let's take a look at energy, since you mentioned that. In fact, I'll open this up a little bit bigger here so we can get a more complete view. And let's go here to where fish are reproducing. Okay, so here's where the fish are reproducing. It does a quick check. A fish checks its own energy to see if it's reached 5 yet. It's just an arbitrary number that's been selected for this model. And if they have, they subtract 2 from their energy. They set their energy equal to whatever their energy is to it minus 2. And because it might have been greater than 5, so they've eaten some plankton. And then they hatch a new fish, right? And then the new hatchling, the little hatchling that comes out, sets a random heading, random 360, okay? And it jumps forward random 3 steps. So that's part of that acceleration out of the gate there. They just go blasting off in some direction. And all this happens instantaneously on the first round. Oh, and the new little hatchling starts off with energy of 2. Now, we could change some of this, but there's one other area let's look at also, and that is where the fish are eating the plankton, because that's where, I think it's going to be over here. Here it is. This is kind of interesting. In fact, let me zoom this up for you so you can see this all. This is where a fish collides with plankton, like when it runs into a little chunk of plankton. What the fish is going to do is increase its energy by 0.5, by half. So the more plankton you eat, the higher energy goes. And then the plankton is just going to disappear. It's going to die. It'll leave the map. Okay? So that's something we can play with right there. The energy that a fish gets from that. If you change that, what are you ultimately changing in this model? If you change the energy they get from eating plankton, and if we saw that plankton is responsible for, the energy is responsible for a certain thing that happens.
Basically, the energy in each lump of plankton, the nutrients in it.
Right, and then what would be the effect? What would you predict if we were to lower that to very low energy?
The fish would have to eat a lot of plankton to survive, and since they're eating plankton at the same rate, they'll probably die out more easily.
So why don't we set it here to 0.1 instead of 0.5? So you're getting about 20% of the energy actually out of this plankton. This is low-grade plankton suddenly. And if you look over here, when the fish is considering reproduction, and it wants to know, has my energy reached 5 yet? If so, have a baby. What do you predict this model is going to behave like now? By the way, we should probably go set those elevations back normal real quickly. Yes? And I'm just real quickly restoring these, up here. Set the altitude to 30. Let's just get this model back into a stable as it was intended, except for one thing. We've changed now just the energy of plankton. Oh, man, that's some low-grade stuff there, I'm telling you. That's pretty sad. I was just seeing in the news recently, someone's engineered a new kind of rice that has a lot more protein in it, and they're starting now to plant that rice over in Southeast Asia. That would be like really high-grade rice, right? I mean, that's a good thing, I think. Some people might not like food engineering, but... So there's that. What would happen if we did the opposite? Anybody want to propose an experiment here? An experiment? Yes, sir? Okay, so set the energy higher. Okay, so like double it maybe to they get 1 or even 2, a full 2 every time they eat a plankton. What do you predict, since this is your idea? What do you predict might happen? It'll do what?
The fish will overrun the plankton.
Overrun the plankton. Oh, I like the way you're thinking. Let's try it out. Here we go. Bring it up for full view. Uno, dos, tres. Ooh, that was pretty. Yeah, you nailed it. They got so healthy, they had so many babies, they ate all the plankton. All right, so you get the idea here how a model can be tinkered with to test different theories or hypotheses, that is. And I encourage you to give this a spin. By the way, Star Logo is a free download. Just go Google it and download it for free and have fun.
Yeah. Okay, and the last thing we're doing, got a spinning. Okay, this is a game. It's called Complex or Just Complicated. So we have a traffic jam and a Dale Chihuly sculpture. Anyone want to venture a guess? Which one seems complex and which one is just complicated? Yes?
I would say the traffic jam is complex because, like they're actually interacting and moving, and there's like each little bus is its own self. Or the Chihuly sculpture, I'm not quite sure about this because I've never encountered one before. But there's like just all these sort of spirals coming out, and it looks like there's a lot of parts to it. But it looks like they're all sort of one thing, and it doesn't look like they're interacting in a certain way.
Okay. Any dissenting opinions? Yes.
I've actually seen a Chihuly, and I would say it is complex because if you think of all the parts that are so different from each other, to be put together and balanced, to be hanging in a light fixture over your head, and to think of the physics of the parts being counterbalanced on each other.
Right.
It is a very complex structure.
Okay, but is it a complex system?
Yes.
Ah. What do you think, Bob? Okay, we're venturing.
Need to be organized to be able to put together. It needs to be somehow organized in some way.
But once it's organized, it's static. So I guess we're arguing that the traffic jam could become static. So there's flexibility here. But the way we were thinking about the Chihuly was that once it was constructed, it was a fixed entity with no more movement. But I think you're right. Some of them probably move and have.
Take them apart and clean them. They put them back
Good point.
together again.
Good point. Okay, next one. We have an early computer and we have the internet. Who wants to venture a guess?
Complicated, complex.
Okay, which was which?
The early computer is complicated and that's complex.
Okay, explanation?
The internet is hundreds of thousands of completely different things basically intertwined with one another. Early computers just, go ahead.
I'm sorry, but then there's like in the early computer, it's not just a computer with a single unit, I mean it is, but then there's also all your transistors that are in there interacting with each other electrically.
But someone put the computer together. So isn't that later?
Like I would say the internet is more complex, but I would say both of them are complex.
Got a point there. Okay, and we were saying that the internet was a complex system and that the early computers were complicated. But yeah, when you take into account all the vacuum tubes, and you have a good argument there. Okay, what about this one? Sheet music versus a human body. Which one is a complex system and which one is just complicated? Yeah?
I think the human body's complex because you have all your arteries and veins in your brain and your nervous system, and it's all interacting together at the same time. And sheet music can look pretty intimidating, but it's just complicated.
Any dissenting opinions? That was good. That was really good. Yay! Okay, one. Okay, how about this? A tornado or a spiral staircase? Any ideas?
Again, I would say the tornado is complex because there's lots of little moving bits of, molecules of air and particles of dust and other things. Whereas a spiral staircase, it doesn't interact at all. It's completely motionless, and once it's all nailed together, like it almost even ceases to become different units. It's like almost all one thing, basically.
Okay, any other opinions?
I think that the staircase is complex just because it's helping you lead down the stairs, so I guess they do interact. And tornadoes just wing, and that's about it.
Tornadoes are what?
Just like basically wings circling around, and they don't really help each other.
Do they have to help each other?
Big, complex.
Uh-huh.
The tornado is totally random, or very much random, and a staircase, after you analyze a little bit of it, you can predict exactly where it's going to go.
Good point. Uh-huh. Any other ideas?
A tornado is an engine. It runs on energy.
Mm-hmm.
It creates entropy.
Okay. And the staircase?
Static.
Static. Okay. That's what we thought. Okay, how about this one? Lightning versus the Mandelbrot set. Which one is a complex system and which one is just complicated?
The lightning is complex because the Mandelbrot appears to be a fractal, so it depends on itself.
Okay. It depends on itself, on self.
Oh, on self.
Uh-huh.
And the lightning appears to be taking the path of least resistance to the ground.
Uh-huh.
And so that could be different depending on the air concentration, depending on the gravity of the ground, depending on if there's a tree or a human there.
Okay. Okay. Well, tell me more about the Mandelbrot set being a fractal. Why are you saying all fractals are not complex systems?
Well, they are complex systems, but they all depend on one thing, so they do have one master thing telling them what to do.
And in this case, what would that be?
It would be the bottom one and the top one, the big two designs.
Huh.
Maybe it's not a fractal, but if they were closer, I'd be able to determine if they're all the same.
Okay. Any other? I heard some people talking over here.
Well, see, the lightning is complex because it's totally random where it's going to strike unless you have a bunch of lightning bolts sticking out of the ground. And the Mandelbrot is complicated, but you can, if you look further into it, it's just complicated.
Okay.
And there's the pattern.
Uh-huh. Arlo?
Like, I don't know, I think maybe when the Mandelbrot set was created, it might have been complex a bit, but right now, I think it's just complicated. And just as a side note, not all fractals have to be self-similar. That means if you look closer, it doesn't have to look like the whole.
Didn't the last lecture say that lightnings were fractals?
Mm-hmm.
The Mandelbrot set has to be perceived like to enter our conscious experience. And that it becomes an interactive process between your consciousness and the mathematics of it, which is infinite. And it's an interactive, evolving, complex system. No one knows what's going to happen in the interaction between the sensible observer or calculator.
I see. Okay.
And the level of the system appearance that you go into.
Okay.
When you press go, you always get the same picture.
Right. Okay, so we were saying that the Mandelbrot set was complicated but not complex, primarily because it's generated by a formula that never changes. It's precisely specified by a formula.
So you're not including chaotic phenomena?
Not. Are you saying using chaos in the sense that if you start out from a slightly different point, you get to a much, yeah,
Right.
yeah.
So you're not including.
I'm not.
So you can just fundamentally break this down into levels of control. I mean, the Mandelbrot set is artificial. We have complete control of what that's going to look like. Lightning, the alternative, same with the other ones.
Well, the lightning is the interaction between particles, right?
But can we artificially reduce it to that level?
I don't know.
I mean, not yet.
Not to a specified level. I mean, they can create lightning in tubes, right?
Not to my knowledge, and you can make the same argument for the tornado and the staircase.
Mm-hmm.
You could try make lightning do the same.
Is it to that extent?
It is actually just on a smaller level because the dimensions of the ball may not be the same or have the same amperage, but it's the same complexity, it's just on a smaller scale.
Can we produce it on a larger scale?
If we have a big enough fluorescent tube.
Well, these are some of the discussions you'll hear among complexity scientists and people studying these phenomena. There is no right and, well, there is some. There is flexibility in the definition, I should say. But thank you very much. I think you all got it. Good job.